Hello everyone. We continue to study the Z-domain analysis module of discrete systems. Today, we start the sixth part, learning of Z-domain analysis method for discrete systems. Section 4, Properties of Z-transform. We mainly study the following related properties. First, linear. Second, displacement. Third, sequence linear weighting. Fourth, serial index weighting. Fifth, initial value theorem. Sixth, final value theorem. Seventh, time domain convolution theorem. Let us first analyze the nature of linearity. The nature of linearity is mainly manifested as superposition and uniformity, which is the familiar homogeneity. The content of the linear theorem is as follows. It is known that the z corresponding to x of k is transformed into x of z. The z corresponding to y of k is transformed into y of z. Then, when a new sequence is ax of k plus by of k. At this time, what is the z transformation corresponding to this sequence? In the form of a linear combination, then the form of its corresponding z transformation is ax of z plus by of z. We mainly focus on the change of its convergence domain. In homogeneous form, then the combination term a, b given here are arbitrary constants. Under normal circumstances, after a linear transformation, the corresponding z transformation convergence domain takes the area common to both. Then it means that it takes the form like this. But in some cases, in some linear combinations, due to the phenomenon of zero and pole cancellation, the corresponding convergence domain may expand. Let's analyze the corresponding example. First, we look at the first example. Find the corresponding z transform of the following sequence. Then, we know according to the form of common sequences, the z transformation corresponding to the unilateral exponential sequence is z over z minus a. And because of our corresponding function form, it can be decomposed into the form of the sum of two imaginary exponential signals. Then, according to this corresponding transformation form, you can see the above sequence can be expressed as the form of the sum of such two sequence z transforms. Therefore, according to the z transform of our known sequence and the nature of the linearity we construct, you can see the first sequence of z transforms to this corresponding form. The corresponding z transformation of the second sequence is this form. We organize accordingly. It can also be organized like this. What about the state of its convergence domain? We take the common area of the two parts of the convergence domain. Similarly, we can also see that for this new sequence, we follow the same method to organize according to the linear nature. Then, the form of the corresponding Z-transform is as follows. The corresponding convergence domain will take the common area of their two convergence domains. In some cases, the phenomenon of zero-pole cancellation may also occur. Let's take a look at this corresponding example given three sequences. First, look at the first sequence. The transformation form is the most basic form of causal sequence. The modulus of Z is greater than A as its convergence domain. We can see the second sequence. Its form can be expressed as a causal sequence minus 1. Such a form of delta of K, according to the linear property combination, its Z-transform is the Z-transform of the causal sequence minus the Z-transform of delta of K1. Then the condition of the convergence domain is that the modulus of Z is greater than the modulus of A. We know that we follow the linear method, construct a new sequence from this x of k, y of k sequence. Then we can see what is the form of its Z transformation. After solving, it is constant 1. A corresponding phenomenon of pole zero cancellation occurs. The convergence domain expands to the entire Z plane. This is a method that uses linear properties to solve the Z transformation process. It is a very special case. I hope everyone gets attention here. Then let's analyze the second property of Z transform, displacement properties. The displacement properties of the Z transform are mainly divided into two categories. The first kind of displacement characteristics of bilateral Z transform. The second kind of displacement characteristics of unilateral Z transform. And for the unilateral Z transform, it also divided into left shift property and right shift property. First, let's look at the shift characteristics of the bilateral Z transform. Shift properties for bilateral Z transform. As you can see from the picture, for the original sequence x of k, if its corresponding Z transform is x of z, then when x of k is shifted on the time axis, whether it is right or left, then we can see according to the corresponding definition of Z transformation. For bilateral Z transform, it solves from k from negative infinity to positive infinity x of k times z to the power of minus k. It is a form of summation. Then that means the value of the sequence involved in the operation is unchanged. What has changed is its corresponding position on the timeline. Then, according to such a form and the definition of bilateral Z transform, we can see after the original sequence is shifted, whether it is right or left, its transformed form is equivalent to based on the original Z transform multiplied by its corresponding shift factor to produce the corresponding amount. In other words, when shifting to the right, the form of Z transformation is x of z times z to the minus m power. When shifting to the left, x of z times z to the power of m. It means the sequence values involved in the calculation of the original sequence of the bilateral Z transformation have not changed. Just its position on the timeline is affected. Therefore, based on the original sequence Z transform, multiplying the corresponding shift factor causes such a change. This is a relatively simple case of bilateral Z transform. Then, let's take a look. Displacement characteristic of unilateral Z transform. If the original sequence x of k itself is a bilateral sequence, then solve it for unilateral Z transform. According to the definition of unilateral Z transform, you can see the Z transform at this time. Then the interval of summation is 0 to infinity. It is shown by the picture. Everyone can see clearly. When seeking the unilateral Z transformation of the original sequence, it starts from 0 to infinity. Then the amount involved in the operation shown in the figure is the red value. Then after shifting this sequence, let's find the unilateral Z transform separately. As shown in the picture, you can see when the sequence moves right, then the equivalent of these two parts is newly moved in amount. Then these two parts are the amount of new shift in. If it is left shift, it can be seen that these two values are equivalent to the amount removed. So, in this case, we seek the unilateral Z transform. Then, its length increases or decreases relatively to the original sequence. According to the definition of unilateral Z transformation, as you can see, as for the right shift feature, we need to increase the corresponding amount. As for the left shift characteristic, we need to reduce the corresponding amount accordingly. So, in other words, according to these two situations, we take the final unilateral Z transform displacement characteristics and carry out the corresponding summary calculation. Let's look at the left shift characteristic first. X of k itself is a bilateral sequence. We find its unilateral Z transform to X of Z. At this time, we perform left shift processing on X of k. Then, in this case, according to the previous lecture, after it finds the unilateral Z transform, it is based on the original X of Z. We need to consider not only the impact of its displacement, but also the removed amount of it. Therefore, the expression of the unilateral Z transform of the left shift characteristic is this expression. But in practice, when we describe the system of discrete difference equations for second-order LTI systems, we encountered two frequently shift expressions, as shown in the slide. The left shift property of x of k plus 1, x of k plus 2, left shift characteristic. Everyone is asked to be familiar with these two results. The above is a general case of it. Let's take a look at the right shift feature. X of k itself is a bilateral sequence. Find the result of a unilateral Z transform as x of z. We perform right-shift processing on this sequence. According to the icon just now, you can see, except for finding the z transform at the beginning, the amount of unilateral z transformation is beyond. Due to the right-shift feature and the newly shifted information, we have to add this part of the amount. In practice, for discrete LTI systems, it is described by the difference equation. The frequently encountered expressions is the form of these two shifts to find the z transform. Right shift characteristic corresponding to x of k minus 1, x of k minus 2. The above general formula need to be mastered. Notes here. For when the Carroll sequence itself is less than 0, x of k is equal to 0. Then at this time, we are asked to find the unilateral z transform for the Carroll sequence. After it is shipped, since no new quantity is added, so it is just based on the original x of z. Just considering the impact factor of its displacement will be enough. It is not affected by the initial value. In other words, it is not affected by the amount of the new shift in. Let's look at a specific example. For a system described by an LTI discrete difference equation, y of k plus 1 second y of k minus 1 equals to x of k plus x of k minus 1. Non-additional excitation x of k. Initial information x of minus 1, y of minus 1. Then find the corresponding response. According to such a form, we take the z transformation on both sides of the equation. Because it is an LTI system, we use the unilateral z transform solution to perform the corresponding z transform, and the right shift characteristic is used. According to the right shift characteristic of the one-sided z transform just now, let's assume that the z transformation corresponding to y of k is y of z. The z transform corresponding to x of k is x of z. Then the corresponding amount of shift here can be expressed as follows. After writing the complete form of the shifted z transform, we bring it boundary conditions. Note that y of minus 1 equals 2 incentive information, x of minus 1 equals to 0. Then, after we bring it in, we sort it out accordingly. You can see the full response expression we sorted out. We finally reduced this expression to such a form. Then follow the inverse z transform, partial expansion method to expand. Find the corresponding expansion coefficient. After getting this form, we can find it. The expression of the inverse z transform is such a result, thus completing the response. Right-shift characteristic of unilateral z transform are the theoretical basis of LTI system for transform domain analysis. I hope everyone can master. Let's analyze the sequence linear weighting. That is, this characteristic form of the left multiplication of the sequence corresponding to the differentiation of the z domain. Assume that the z corresponding to x of k is transformed into x of z. Then the sequence of multiplying k in the time domain by the corresponding z transform is differentiated in the z-domain. Multiplying ak in the time domain is equivalent to finding a differentiation in the z-domain. Then we can promote the same reason. If you multiply k to the power of m in the time domain, then in the z-domain, it is equivalent to finding the mth differential. We use this symbol for corresponding representation. Then everyone can see the result represented by this symbol. This is expression. Everyone will use this expression to solve the problem. Let's look at a specific example. Find the z transformation x of z corresponding to this formula. Then it is known that the z transformation corresponding to this formula, z over z minus a. The modulus of convergence is that the modulus of z is greater than a. We multiply the sequence in the time domain by k. So what form is its z transformation? According to the definition just now, we can see to get the partial derivative of the z transform of this original sequence in the z-domain, then we sort out after solving. The final result is this. This is the change of its corresponding convergence domain. Next, let's analyze the nature of sequence index weighting. Equivalent to the scale transformation of the domain, then we look at the content of this nature. It is known that the z corresponding to the original sequence x of k is transformed into x of z. Then the original sequence is multiplied by the unilateral exponential signal in the time domain. The corresponding z transformation is equivalent to the scale transformation in the z-domain. A is a non-zero constant. We must pay attention to the change of its convergence domain. According to the scale transformation characteristics of the z-domain, we can look at two special cases. If the unilateral exponential signal A in the time domain is multiplied by the minus k power, then the corresponding scale factor becomes A. If you multiply minus 1 to the power of k in the time domain, then it is equivalent to x of z inversion operation in the z-domain. These are two special cases. I hope everyone will pay attention. Let's look at specific examples. The z transformation expression of this sequence is known as follows. Now we build on this complex sequence. Multiply it by a beta to the k's power. What is the z transform of this more complex sequence? According to the nature just now, we can see that the exponential signal is multiplied in the time domain. It is equivalent to the corresponding scale transformation in the z-domain. The scale factor is beta. We bring it to the organize. You can see that this is the final result. Notice the changes in the convergence domain, because the scale factor has changed accordingly. The convergence domain has also changed. Similarly, if we add the scale factor to another sequence, then the transformation is very similar. The final result is such a result. You can look at the corresponding comparison. Then let's analyze another property, initial value theorem. This is a very useful theorem. It applies for the right sequence. First, x of k is a Carroll sequence. We know that its Z transformation is defined as follows. Then, what is the initial value at this time? The initial value of this sequence of x of 0 can be transformed by its corresponding z. Find the limit where z tends to infinity. This is the initial value of x of 0. What is the initial value of x of 1? We know that x of 1 can be written as x of k plus 1. K is equal to 0. According to the shift characteristics of the unilateral sequence, knowing that the unilateral z transform of x of k plus 1 is such a result. So we can use this expression for its initial value. Solve for the limit where z tends to infinity. Let's look at a specific example. The known x of z expression is as follows. We are required to find its initial value x of 0, x of 1. On the basis of not seeking the inverse z transform, we use the result of the transformation. It is convenient to use the initial value theorem. Solve the two initial values of x of 0, x of 1 accordingly. X of 0 can be expressed as x of z. Z tends to the infinite limit to solve. X of 1 can be multiplied by x of z, x of 0 times z. Solve by the limit where z tends to infinity. After we brought it and sorted out, we got the values of 0 and 1 respectively. Pay attention when using the initial value theorem. To solve the initial value, the limit sought is the limit where z tends to infinity. Let's look at the final value theorem. The final value theorem also applies to the solution of the right sequence. For the Carroll sequence, we know its z transform form, which is the form of its unilateral z transform. At this time, we come to find the final value of this sequence. Then, according to the corresponding analysis and proof, we can use the following expression for the final value of this sequence to solve. That is, z minus 1 times x of z. Find the limit where z tends to 1. Then, it should be noted that in the time domain, when k tends to infinity, only when the original sequence x of k converges can the final value theorem be used. Then, how to determine the final value theorem of x of z? Is it applicable? We need to judge based on the limit where z tends to 1. Then, in most cases, the form of the final value theorem is expressed as this corresponding expression. We need to find the limit where z tends to 1. Let's take a look through specific examples. What characteristics does it have? What kind of sequence final value exists? This column is some common sequences we have given. This is the case of determining whether it has a final value in the time domain. Let's separately transform the z in form of these common sequences. Then we found that in the case of Carroll sequences, its convergence domain has a different convergence radius. We can find that the modulus of a regular z is greater than 1. In other words, the modulus of z is greater than 0.5. In both cases, convergence domain contain unit circles. We find that its final value exists. So, is there such a rule? Through corresponding analysis, you can find the conditions for the existence of the final value. The following form can be used to judge if the pole of x of z is inside the unit circle. Then it means the position of the pole determines the radius of convergence. The rightmost pole determines its convergence radius. If the convergence radius is less than 1, then it means that the convergence domain contains the unit circle and the final value exists. This is a very useful rule, and it is also a very intuitive rule. We can use the distribution of poles to determine whether the final value exists. In other cases, if the pole is on the unit circle, then it can only be located at z plus z equals to 1 and is the condition of the first order pole. In other cases, the final value does not exist. In summary, the final value theorem requires that z equals to 1 be in the convergence domain. Then it means that the position of the pole must be inside the unit circle. The requirement is a distribution of a value greater than or equal to 0 and less than 1. Let's take a look at the time domain convolution theorem. It is known that z transforms of two sequences exist separately. Then these two sequences find the convolution and the corresponding z transform in the time domain. What form is it? We have proved through analysis. It is the product of the z transform of these two sequences. Under normal circumstances, we need to take the area where they overlap. Then, according to the time domain convolution theorem, the problem of convolution is hard to transform into the problem of multiplying two sequences by z transform. This time domain convolution theorem is the theoretical basis for transform domain analysis. Z convolution of two sequences in time domain equals to the product of two sequences of z transforms in z domain. This is a very useful property in some special cases due to the fact that some poles and some poles of the linear combination may cancel. The convergence domain may expand. Let's look at a specific example. The two sequences are known. We need to find their convolution sum. We use the transform domain analysis method to solve. First, the form of transformation corresponding to x of k, h of k, solve separately. Convergence domains are the modules greater than a and the modules greater than b. Then, according to the time domain convolution theorem, the z transformation corresponding to y of k is the form of multiplying x of z and h of z. After getting this form, if we want to find y of k, we only need to inverse the z transform of y of z. Next, we find its inverse z transform. Then, according to the change of its convergence domain, these are the two first-order poles. The convergence domain is determined by the position of the largest pole at the outermost. In other words, its convergence domain is larger than the outermost area outside this circle, we found the inverse Z transform for partial fraction expansion. The expanded results are as follows. After expansion, look up the table using the inverse Z transform table. The expression of y of k is as follows. Then from this we can see it is very convenient to use the content of the time domain convolution theorem. The problem of the two sequence convolution are solved. The calculation of convolution sum is simplified, but at the same time increase the amount of Z transform and inverse Z transform operations. In this part, we mainly introduce the relevant properties of the Z transformation. I hope you can focus on the shift characteristics of the Z transform and the content of the corresponding time domain convolution theorem. These two properties are the theoretical basis for the Z domain analysis. Thanks, that's all for this lesson.